In this talk, I'm going to discuss oxygen carrying capacity and transport. The amount of oxygen that can dissolve in blood depends on the partial pressure of oxygen and its solubility. So what I'm looking at here is the content of oxygen equals solubility times pressure. Solubility is approximately 0.003 milliliters of oxygen per 100 milliliters of blood per millimeter of mercury, sometimes called volume percent. PO2 is 100 millimeters of mercury, then blood will carry 0.3 volumes percent of oxygen. This is not enough to support metabolism. However, each hemoglobin molecule can carry 4 molecules of oxygen, and when fully saturated can carry 1.34 milliliters of oxygen per gram of hemoglobin. Normal human blood contains about 15 grams of hemoglobin, for a male, females a little bit less, per 100 milliliters of blood. So 1.34 times 15 gives us about 20 milliliters of oxygen per 100 milliliters of blood, much more than the 0.3 in the absence of hemoglobin. So let's assume now, for this example, I've got 2 compartments with a semi-permeable membrane that is permeable to oxygen. And at this point, there are 5 molecules of oxygen on this side and 5 over here. So my N equals 5 in both sides. If I drop a hemoglobin molecule into this compartment right here, it will pick up 4 of those molecules of oxygen, leaving only 1 dissolved. Now oxygen is 5 times higher on this side than this side. Oxygen will begin to move. Now we've got 3 and 3, but the total amount of oxygen carried is now 7. 3 in solution plus 4 in hemoglobin. If I drop another hemoglobin molecule, it will bind those 3. Now I've got 3 molecules of oxygen on this side, essentially none over here because they're bound to hemoglobin. So one of those will move over, bind to hemoglobin, another one will move over, and so we now have 1 oxygen molecule dissolved on this side, 1 on this side, but the hemoglobin contains 8 molecules. This side now has 9 molecules of oxygen compared to this side. What that means is that hemoglobin is increasing at least the apparent solubility for oxygen. By binding the oxygen to the hemoglobin, it's reducing the partial pressure of oxygen, allowing more oxygen to come in. This is the oxygen-hemoglobin dissociation curve, and we're going to talk about this in a little bit with the computer model. What I'm putting here is something called P50. P50 stands for the partial pressure of oxygen required to reach 50% saturation. And we'll talk a little bit more about the P50. If the curve moves in this direction to the right, the P50 is going to be higher. If the curve moves in this direction to the left, the P50 will be lower. Now I'm going to leave this up here. You can pause the program. You can read through these bullets if you wish. I'm not going to go through them. Now I'm going to open up the oxygen transport simulation. In this model, I'm displaying the oxygen dissociation curve here. This little blue line here is the P50. It's at about 25 millimeters of mercury to reach 50% saturation. I can adjust the PO2 to see where we would be on the curve, here at 60, back to 100. If I increase the temperature, it's going to drive oxygen off hemoglobin, so hemoglobin affinity is going to go down. If hemoglobin affinity goes down, it means that the partial pressure of oxygen needs to be higher to get to 50% saturation. So let's try that. So we're now looking at this right shift. The P50 now is up around 37 millimeters of mercury in order to reach 50% saturation. Decreasing temperature causes the hemoglobin to have a higher affinity for oxygen. It takes less oxygen to reach that 50% saturation. The PO2 here is at about 18 millimeters of mercury. Under acidotic conditions, oxygen is also driven off the hemoglobin, and that causes a shift also to the right. Hemoglobin has a lower affinity because the hydrogen ions are driving oxygen off, which means it requires more oxygen to reach that 50% point. And alkalosis has the opposite effect. Now, if I increase the hemoglobin concentration, I see nothing happening. The content has gone up. It's now up to 30 volumes percent. But there's no change in the saturation. Saturation depends on partial pressure of oxygen, not on hemoglobin concentration. At this point, I'm going to switch to oxygen content. Now I'm looking at oxygen content here at about 20 volumes percent, and there's my PO2 again. And this tiny little orange line here, it's hardly visible, is the dissolved oxygen, 0.3 milliliters of oxygen per 100 milliliters of blood. Now if I increase the temperature, we still see a right shift. If I decrease the pH, once again, we see the right shift. Now, however, if I increase hemoglobin content, we see oxygen content rising. More hemoglobin, more oxygen. Decrease hemoglobin, now we have a severely anemic individual carrying very little oxygen on the hemoglobin. I'm going to do one more thing. I'm going to add carbon monoxide to this situation, and I can raise the carbon monoxide. Let's bring this up to 40%. So now I have 40% of the hemoglobin bound to carbon monoxide. This isn't 40% carbon monoxide. That would long ago have killed you. This is 40% of the hemoglobin containing carbon monoxide. 60% then contains oxygen. We can see then that the content of oxygen has come down. Carbon monoxide binds to hemoglobin about 250 times more strongly than does oxygen. So a little carbon monoxide greatly reduces the content of oxygen can be carried by hemoglobin. Now let's increase the hemoglobin concentration. 40% of the hemoglobin is bound by carbon monoxide, but now I've got more hemoglobin, therefore more oxygen. Another thing to notice is the shape of the curve has changed. So I'm going to split the two effects of carbon monoxide and hemoglobin concentration. So let's go back to this 40%. I now have my 40% of hemoglobin bound to carbon monoxide, and I'm going to also make it anemic. The individual is now anemic to the point where the two curves line up. So in each case, we're down to about 12 volumes percent. But notice the difference. When I bring down hemoglobin, the shape of the curve remains. We still get this sigmoidal shape. However, in the sample in which I just raised carbon monoxide concentration, we now see the shape has changed. Carbon monoxide binding to the hemoglobin tends to alter its properties so that it looks more J-shaped than S-shaped. Well, that concludes this section on oxygen transport. I will continue discussing oxygen transport in later segments.